So just to reiterate, carbon is necessary for plant growth, and the presence of carbon in the soil as decomposed organic material is important for an increase in water holding capacity and nutrient holding capacity of the soil. But we also care about the carbon cycle because the imbalance between pools, the imbalance between atmospheric carbon and carbon that can be utilized within the ecosystem, is resulting in a relatively rapidly changing climate when looked at historically, a change that has really far-reaching effects in terms of ecosystem function. This slide just shows an illustration of how chemical nutrients cycle through the forest ecosystem. We'll take each of these processes in turn with the next few slides. The nutrient cycle is similar to the carbon cycle in that soil nutrients may enter or leave the system through several means. Nutrients enter the soil as a result of weathering and soil formation, but also as a result of biomass decomposition. Nutrients may also be deposited from the atmosphere, but these chemical elements that are deposited are typically not in a form that trees can utilize or plants can utilize. Something that we've gone over before, the nutrients that are recycled in the system are of most importance because they are in a form readily usable by plants and trees. The term nutrient mineralization refers to this process of freeing up mineral nutrients from organic matter in the soil through the process of decomposition. Nutrients can also be lost through the system through a variety of means as well. Nutrients may be lost through the system as a result of soil leaching. They may be lost as a result of an actual physical loss of soil through the process of erosion. Nutrients may be lost also through the removal of plant biomass during harvesting. But also nutrients can be lost through the process of volatilization, which could occur during a significantly hot fire. And so we care about the nutrient cycle because the presence or lack of available nutrients directly affects the ability of a site, the ability of a forest to grow trees, to grow plants. The nutrient content of the soil influences what can grow and how well it can grow. As foresters, we can have a significant impact on the nutrient content of soil. It's difficult to add additional nutrients through something like fertilization, though that practice is becoming more common among industrial landowners who grow trees on a really short rotation in plantation settings. This is becoming more common, particularly in areas of the southeast. But typically, we don't do a lot of fertilization as a matter of course in forest management. But through conscientious management, through purposeful management, we can protect the ecosystem processes that result in nutrient availability. Specifically, we can protect soil organic matter. We can do this by leaving enough woody debris and biomass behind during harvesting to ensure that this process of nutrient cycling is not hindered by our actions. It's not the natural course of nutrient cycling is not hindered by our removal of biomass. And this brings us to forest succession. The process of forest succession refers to the developmental steps of a forest over time, beginning with a stand replacing disturbance, or beginning with a non-forest setting, and essentially culminating with the development of a mature, what could be considered a resilient, self-replicating forest. And we'll talk a little bit more about that in a second. As foresters, we often implement management to maintain one successional stage or another, depending on the goals of our management. The first stage of succession is referred to as the stand initiation stage. Following a major disturbance which eliminated the previous stand, there's a period of time where site resources are not yet limited. Shade-intolerant species typically occupy this stage of development. Species that are adapted to occupy a site readily and adapted to grow quickly in open growing conditions. Species that are adapted to put on height growth really quickly. The second stage of forest succession is referred to as the stem exclusion stage, and this stage begins with competition for these limited resources. It occurs when competition essentially begins. The trajectory of a forest stand, of an even-aged forest stand, and one in which there are many young trees at stand initiation, on the order of thousands of seedlings per acre. Over time, some trees outcompete others, resulting in fewer middle-aged but larger trees per acre, on the order of several hundred trees per acre. The stem exclusion stage is a period of time where trees are outcompeting trees in the same age class. So if you have a stand of trees that are a cohort, they're a stand of trees that were established following the same disturbance, it is essentially an even age stand, though there's some variability in ages between the stems. Ecologically speaking, they're about the same age. And so as these trees grow over time, some of those trees win and some of those trees lose through this competition. And it's a function of limited site resources and the competitive ability of certain individual trees within that stand. The third stage of forest succession, referred to as the understory reinitiation stage, occurs as natural disturbances alter the forest structure. So again, we're thinking of the same even age stand. As that stand is developing over time further, natural disturbances occur. There's small wind throw events, small blowdown events. Wind throw is really the most common natural disturbance here in western North Carolina, also up through New England as well. And this results in small gaps in the canopy. New groups of plants become established in those gaps, and you begin to see the development of multiple vertical layers of vegetation within the stand, the development of vertical structure within a stand. So the main canopy still consists of this initial cohort of trees, and an understory layer of primarily shade-tolerant species that have become established following these small canopy-altering disturbances become visible as well. The final stage of succession is referred to as the climax, or steady state stage. There's considerable debate among forest ecologists regarding how steady this state actually is, and whether it really should be considered the end of something by calling it, the climax portion of succession. Is probably a misnomer. It's probably an improper term, because obviously things are changing all the time. Nothing is really steady in a forest ecosystem, and so the new trees are becoming established all the time through a variety of disturbance events. But theoretically, this stage of forest succession, towards the back end of succession, where we're starting to see what you would consider a mature piece of forest land, theoretically, this is a self-replacing state that continues on until another stand-replacing event occurs, and at which point we'd start all over again with all the other steps, right? A stand-replacing event could include something like a major wind event, or an ice storm, an insect or disease outbreak, a stand-replacing wildfire, basically anything that removes the main canopy within that stand, which would set you back to the stand initiation stage. The nature of stand replacing events varies by ecosystem and varies by biome. This is what we refer to as the natural disturbance regime of an area. As an example, stand replacing fire is really not part of the natural disturbance regime of the southern Appalachians, whereas major ice storms can be. So in this stage of succession, you begin to see the development of multiple age classes of trees within one stand. Because trees are larger, the small-scale but frequent disturbances result in larger canopy holes. And so this uneven age structure is really what results in the eastern hardwood region, southern Appalachians up into New England, if stands are left to develop over an extended period of time. Again, following a stand replacing event, this whole process starts over. When we harvest trees from a forest ecosystem, the ecological effects can be far-reaching. First, I should begin by stating that it is entirely possible to harvest trees and simultaneously protect soil and water quality and the ecological integrity of a forest. This is why forestry operations should be planned in a really meticulous manner to ensure that that is possible. But it's important to recognize when we enter into discussions of sustainable forestry, of proper forest management, that we acknowledge the fact that the concept of sustainability must extend beyond the concept of sustainable wood production or sustainable fiber production. From an ecological perspective, the impact of harvesting operations on soil is more substantial than the impact on vegetation typically. Trees grow back, but they don't grow back without quality soil. Trees develop on the order of decades. Soil develops on the order of millennia. To put it another way, the process of soil formation is so slow, it's slow enough that when we damage soil or lose soil through poor land use practices, we can consider that an irreplaceable resource, a finite resource. With that said, the seasonal timing of harvesting is important. When soil is compacted, roots have a hard time growing, and water has a hard time infiltrating, resulting in erosion, resulting in accelerated erosion. When we operate heavy equipment, skidders, bulldozers, mechanical harvesters, horses, whatever, on wet soil, compaction is inevitable. This can be mitigated by harvesting only under favorable soil conditions, either frozen soil or dry soil. In New England, we had this really wonderful period of time during the winter where the ground would be frozen solid for months, and we could operate equipment with minimal compaction during this time frame. In the South, things are different, and you really need to be operating only when soil is dry or significantly dry. Different types of equipment results in different soil impacts as well. The goal is to choose the equipment most suited for the soil conditions, most suited for the site conditions. We'll get into specific harvesting systems, different mixes of equipment, and how that all works later in the semester. But just for now, you just need to understand that there are ways to choose different pieces of equipment and different types of harvesting systems to be lighter on the land, to minimize the impact of that harvest. As I mentioned earlier, nutrients may be lost from the system through erosion and through the removal of biomass. Those are two of the ways where it can occur. We can mitigate this during harvesting by avoiding accelerated erosion first through proper road and skid trail layout. For you guys where some of this terminology is a little bit new, a skidder is what's moving the wood, the cut trees from the stump to the landing where a truck is going to pick it up. The skid trail is essentially what the trail that skidder is following out of the woods. By planning the layout of roads and by planning the layout of these skid trails, and by sometimes altering the silvicultural system that we're using, the management system that we're using, we can take really huge steps towards avoiding accelerated erosion. One of the primary things we could do is to leave unmerchantable material in the woods, tops, limbs, branches, things that are not to be sold for a product. They're more valuable ecologically staying in the woods, as to be decomposed, to be broken down, and to also protect the mineral soil from erosion during the operation of equipment during the harvest. In conclusion, sustainable forestry requires an understanding of ecosystem function. As foresters, we need to be able to square our management goals with the limitations of the ecosystem. Often our management objectives are really determined by economic, social, or political decisions. As foresters, as natural resource managers, we have an obligation to develop an understanding of forest ecosystem function, recognize the ecological effects of the disturbances we introduce to achieve our management goals, and we also have an obligation to measure the sustainability of our actions against all components of the ecosystem. As we discussed within the biome lecture, organisms are resilient generally resilient to the ecological disturbances they evolved with. When our actions as natural resource managers result in less ecological resilience, the sustainability of our actions become questionable.